Commercial concentrated aqueous ammonia is 18% ammonia by mass and has a density of, what is the molarity of the solution? So remember, molarity is equal to moles divided by liters. So the things that we want to know are the number of moles of ammonia that are in there, and then we also want to know the total liters of the solution. We got to find those two things to be able to find the molarity. It gives us a percentage right here, and then we can make an assumption from the percentage that that means that we have 18 grams of ammonia per 100 grams of solution, because that of course would give me 18%, which it tells us is an 18% solution. Since I have 18 grams of ammonia, I can now convert that to moles, and then since they give me the density of the solution, maybe you remember this, maybe not, the density is equal to mass divided by volume. If I know my density and I know my mass, my density and my mass right here, I can find the volume of the solution. So two triangles right there help you get the needed information to find the molarity. So first of all, let's convert 18 grams of NH3 to moles. And if I add up NH3 on the periodic table, it adds up to 17 grams of NH3 in 1 mole. So dividing those can be a little bit more than 1.058 moles of ammonia. So that's going to end up going on the top of my equation right here. And then I'm going to divide it by my liters. So my volume is going to be equal to mass divided by density. And so my mass is 100 grams of solution. And I'm going to divide that by my density, which is 0.8 grams per liter, or grams per milliliter, grams per milliliter. Careful of that, grams per milliliter. And so then I end up with, dividing those two, 125 milliliters, which I have to have it in liters, so 3 to the left, 1, 2, 3, gives me 0.125 liters. And that goes in down here. And 1.058 divided by 0.125 ends up being 8.47 molar for the solution. Number 2, a reaction important in the extraction of iron from iron ore is, and then they give you a Kp right here, so equilibrium constant for pressure. If at this temperature CO gas is initially present at a pressure of 0.9 atmospheres, calculate the pressure of CO when equilibrium is reached, and calculate the K of the reverse of this reaction. Alright, so let's rewrite the reaction over here. Notice this is a solid. CO is a gas. And then we have Fe solid over here again, and then we have CO2, and that's a gas. And we can write an initial change equilibrium table right here. And we're told that CO gas is initially present at 0.9 atmospheres, so I can fill that in right here. This is a solid, so it's not going to be involved in the equilibrium expression. Same thing with this one right here. And I can assume that there's none of this to start with. When the change occurs, I'll lose x of this and I will gain x of this, because notice it's a 1-to-1 ratio. So I'll end up with 0.9 minus x here and x right here. And then I can set this equal to the k sub p. And it tells me that Kp is equal to 0.4302. And that's equal to products raised to the power of the coefficient of 1 divided by reactants. So that would be 0.9 minus x right here. And now I need to do just a little bit of assuming. Let's assume that this x is small in comparison to 0.9, because now that all of a sudden makes it like super easy to solve. And then when I solve this for x, I multiply 0.4 times 0.9, and I end up with 0.387 atmospheres as my pressure of CO, because X is equal to CO2 right here. And so 0.387 atmospheres is my pressure of CO2. Now, the second question says calculate K for the reverse of the reaction. And remember, when you reverse a reaction, you do the inverse of the K. And so the K of the reverse of this reaction would be equal to 1 over the 0.4302. And so if I take the inverse of that forward reaction, I'll end up with 2.32. No units go on there, but that would be the K for the reverse of the reaction. More on the next video.